But the reason why 9-1 has a higher chance to pop up out of twin primes is that 9-1 isn't fighting for any other spots, while 1-3 is fighting for primes with primes 7-9 every time on the times 15 racket, which is what I go on about here. But okay, come back. Does this mean that we're going to have to rewrite math if we do consider -1 a prime? I don't think so, because inherently humans have, about when an imaginary number is supposed to be there, but we subtracted it on how we think ratios work. It's ironic how we wanted an imaginary number and we came to the assumption that it equals -1, and that we use algebraic formulas and stuff using -1, when -1 might be is highly possible that it's a prime, because every prime, when you subtract itself on the number line, will land on 0, and then when you subtract itself again, it will always jump over -1, essentially never being able to divide -1 or being able to land on it whatsoever. But then -1 takes out every negative number behind it. So going negative, there's only one prime, but going positive, there's infinitely many primes. And this right here shows us all given spots where twin primes can exist. And essentially, I know where every spot where twin primes can exist, and you can go and test this out yourself by just looking up twin primes. And then the rule to follow on this is right here, any twin primes ending in 1 or 3, the very next 5 will be a number divisible by 15. 1, 3, 5. Any twin primes ending in 7, 9, the 5 before them will be divisible by 15, and here, and here. And then the rule for and these are odds, and then the rule for the even numbers times 15, which will be 30, which is 29 and 31. The number in between them will be divisible by 15, and that's true, it comes out to 2. But even though I can prove that there are infinitely many spots for twin primes, I don't know if I'm at the point where I can prove that twin primes are infinitely possible, because we don't know if there's a point where something clicks to where we know that, according to the math, that there's infinitely many gaps of 16, which when I think about it, it tells us about the Allen-No, which is essentially the Allen-No number, which is a number that counts in infinite sets, and an infinite amount of sets, and each of these sets are infinite, which is essentially what's happening on here with the numbers. Is I have infinite sets, and these infinite sets are forming to tell me about primes. And all of these numbers will follow the 1-2 ratio, whether through, because here's 2 possible primes to 1 definitely not possible, 2 possible to 1 definitely not possible, or just adding 3. So if I plug in 2, that would be, or odd numbers because we're working with odd numbers, 3 plus 1 plus 2 is 3, 3 plus 6 is 9, 5 plus 10 is 15, and 7 plus 14 is 21, 9 plus 18 is 27, and that's what's happening on getting these numbers right here. And that's why those numbers are popping up. And okay, and I think that's it for now. But the reason primes are, let's say every odd number from 3 and beyond has the potential to be a prime, but the only reason any other odd number is knocked out is because of previous primes before them are set up in such a way that they keep knocking out every other odd number, because essentially because we're doing the 1-to-2 ratio, so the prime 3 is 6. What we do is keep adding the 6, and that's what's causing those patterns there, which 3 is 9, 15, 21, but then we're doing it with each prime, 14. But essentially this shouldn't really break any formulas that rely on Euclid's discoveries or anyone else's that's well proportionate, well, evenly distributed to where they can find the patterns in whatever they're finding, such as, like, there's a number about 60s, and right here we see that if we jump gaps of 60, 60, 12, we're getting numbers that could be odd when they're divided just from starting from 2. Same thing for here. 22 plus 60 is 41. But essentially this is how numbers work. And yes, it'd be nice to understand this so much that you can look at a number line and be like, oh, that's prime for sure. But the thing is, when you play a game of Minesweeper, if the primes are mines, when you play the game Minesweeper, you don't want to find the mines, you want to find where they're not, so that you understand where they are. And that's essentially how we're finding this is the best method to find primes, because if we know all possible spots where they're not, it only leaves us the gap of where they are. And I just seen James Grimes talk about Bayes' law, or Bayes' statistic. He said as he keeps getting more information and adding to it on where he wants to find fixed spots, he can get to where he's always finding the fixed spots. And that's what's happening here for the number line that was 333. If we go through and find all the other numbers that land on 3, we can essentially just keep knocking them out to where at the end of the data sheet, any numbers coming out will always just be primes as we keep finding primes and adding them to the pattern. Every time a prime pops up that we don't know, well, essentially that we haven't thrown into the pattern, we throw it in and it'll start shooting out only primes again, or it'll keep shooting out primes to where we're doing that. But earlier I was talking about Alan No, and essentially we're trying to understand these infinite sets that are taking out there's infinitely many of these sets taking out twin primes, and we're trying to understand all the sets to where we understand whether twin primes are possible or not possible. And the person I seen make a video about Alan No's was saying that an Alan No is so beyond our comprehension that we can't fathom to comprehend it. But mathematicians are sitting here and knocking down the gaps between primes from 70 million all the way down to an infinite gap of 16. So as we keep reaching to 2, we are essentially understanding the Al No number, and then with this, it proves that the twin prime conjecture is not a lost cause, and that the more we start to understand the primes, the more we'll be able to understand, or the more we can start doing more fine tuning to our problems and understanding why our mathematical formulas work or are failing. And to me, we might, even though this essentially says that -1 still works as a prime, we might be able to acknowledge it as a prime, but does that mean we should change its use as an imaginary number? Because primes are a key factor in formulas, and somehow we still was able to stumble on to -1 being essential in an imaginary way, which turns out to be true, and this confirms that. And then I mean, I don't know how to break this down anymore to show you that the Riemann hypothesis is true, even for the fact that, say, you just want to know a number that's 1,233,000, the 120,023rd number that is divisible by 7, that is in the number 7 line. You plug that number, you plug that number into here, and then it'll give you start with the prime 7, and then you plug the 1 million, and as you keep adding, you will know any and all spots of 7. Same thing and then the only reason for changing it up a little bit is to alter it on the number line, which is essentially because this times 2 is 2, 4, what was we saying earlier? 1, 2, and if we do it with 7, equals 14 plus 14 plus 14. That's what's happening here. 0 plus 14 plus 14 plus 14 plus 14. And I'm very apologetic for glossing over all of this extremely quickly, but I hope to be able to talk to more people in the math community and more people who would like to discuss more of these patterns and stuff, because some of these patterns I've only started discovering in the last week or two, and then I've been working on this for about 2 years now, 2.5, and I didn't have the breakthrough that led to all this until about 6 to 8 months ago. And I'm still discovering new things about this, and and I know what all this means is that it proves the Riemann hypothesis. Whether it proves the formula to be true or not, I don't know entirely. But I know that all squares are boxes, but not all boxes are squares. All of the Riemann zeta function is the Riemann hypothesis, but not all of the Riemann hypothesis is the Riemann zeta function. The Riemann zeta function is just a byproduct of the Riemann hypothesis. A square box is only a byproduct of the existence of boxes. So there's not much more clarity that I could add to this at this given point in time. And I would like for anyone to give me feedback. And I apologize for the poor video quality or anything. I don't really make YouTube videos, and this entire time I've been nervous. And there's not much more I can really add to this, so thank you for anyone who's watched this video, and hope that this reaches the right ears. Thank you.